Okay. All right, we are back on part 2, and we're going to look at a couple more, one more note to make, and then we're going to check our homework. All right?
You said and you said bins, and you just said.
He was wondering if the binomial or binary.
Oh, which one?
I know now.
Yeah,
I was making sure. It means binomial, right?
Okay.
It means binary.
All right. Jot down this example, and let's see how we will discuss it. I'm going to try to go down the same path that we just went down, but we're going to hit roadblock. So let's see what the roadblock is. All right, there are 10,000 CDs in a company sitting there, so 10,000 CDs total. The word is that 10% are defective, so write down this example. And I'm going to do a simple random sample of 10. So I'm just going to pull 10 out of all those CDs. So I am wondering, of those 10, what's the probability that there are no defective ones? So I'm going to say that X, my random variable, is the number of defective ones in the group. And I want to know what's the probability that X is 0. Before I do that, I have to check the bins, and this is where we're going to hit a roadblock. Do you see where it's going? Maybe not.
Oh, it's not placed.
Right, so when we take a simple random sample, are we throwing the first one back that we chose? We are not. So where is this going to fail on our bins then, Caleb? B-I-N-S, it's definitely binary, defective or okay. It's independent, sort of. Maybe we won't check that one. The number of trials is 10, but what about the I and the S? I heard you have kind of infer about it.
Then it's different because then it'd be out of 9,999 instead of out of 1,000.
Right. So if we do the probabilities, actual probabilities, the probability of doing the first, getting a defective, I will say of getting this, I said was the probability of getting defective would be, what's 10% of 10,000? 1,000? So it takes me a while here. So if we had the probability of getting, let's say the probability of getting 10 that are okay. So that's what the probability is of no defects. So we have okay, 10 times. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 okays. So the probability of getting an okay one in the first one, if 10% are defective, 10% means out of this, 1,000 are defective. So how many are okay? No, I can do this. 9,000. All right. And how many total? So this is the number, that's the probability on the first draw of getting an okay CD under these parameters. 9,000 over 10,000. But then what happens on the second draw, Allie? It's no longer this total here anymore. So what is it?
It's over 9,999.
Right, so we've taken one out. That was the first one we pulled out. So how many okay ones are left? Take a 1 from that.
8,199.
Right. All right, keep going for us there, Allie. So on the next draw, there are
9998.
Right.
8998.
Yeah. So and so on, and that'll go all the way down to the very last draw, which I did, and it was 8991 on the top, and there was 9991 on the bottom. So I'm not going to write all 10 of those out, but do you see that the probability is not the same for each one of these? So when I actually put all these numbers in, even the ones that I missed with the dots, I got 0.3485. So I actually did this problem. Now I'm going to go back and do something that may surprise you. So we'll see. Let's look and see if this works as a binomial distribution anyway. Even though it doesn't pass the muster here, it does not have the same probability. They are not totally independent from one another because of this difference. let's pretend it is a bin situation. So, on your calculator, we are going to find the probability of x equals 0. So we go second bars. Find down your list the binomial. Well, it would be a PDF. Remember we use P when it says equals, and we use C. I would love to know what that stands for. I've read the book, I've looked it up online, I've asked other teachers. What does it, somebody tell me, do you know? Is it that obvious and I don't know?
I feel like you'd be the only person in the school that actually would know. So
C
Well,
stands for continuing.
So P, this means equals, but I could kind of say continuous for this, but P.
That's a point.
Point at this point. All right, I'm going to take that and go with it. The reason why they put a P here is because this means at one point, and the reason they put a C here is it's continuous. I don't know why, but I'm going to pretend I do. All right, so what are the little parameters? Bailey, what are the little parameters that follow when we put this in? What is it? Numbers, probability of success, and X. So what will go in
the
for this?
trials will be 110.
The trials, they're 10. We're going to draw out 10 CDs, so that's 10. And what's the probability of defection? Defective?
10%.
Defection. Not defection. Of being defective, what?
0.1.
Right, 0.1. And we want to know what the probability is of no defects in those first 10. So, what does it give you?
0.348687.
Yeah,
All right,
7.
so we're off by 10, 100,000, 2 10,000,
87.
20,000.
0.3487.
Oh.
Yeah.
All right.
Yeah.
Oh, I'm
She
sorry.
did.
I was
Okay.
wondering what your hand was down
All
there. I
right,
thought
this
45.
is the one, this is the true one, and this is the one the binomial distribution gives us. So, there are some cases when we take a simple random sample, which without replacement, where we are allowed to say that it's a bins when it's not. And here's the test for that. Put it over on our little list. We can use the binomial distribution for a simple random sample when n is large. Come on, come on. What are you supposed to say?
What do you mean by large?
Alright, when n is large, so here's a test for this. When you're testing this, here's what the book says, here's what I say, tell me which one makes sense to you. I'm sure they mean the same. The test is that n, little n is the sample size, is less than 1/10 of the whole population. I'll say n, big N for the whole population. In this case, the number was 10,000 for the whole population. So, is little n less than 1/10 of 10,000? Well, 1/10 of 10,000 is just 1,000. Is 10 less than 1,000? So it does. But I like to think of it this way. Mathematically, these statements are the same. The population is greater than 10n.
Did we have to know that for our homework last night?
I think on the last one we
Yeah.
did. So I'm going to have to retract that one. All right.
I thought
So-
n was supposed to be large though, we're just saying n has to be small.
Pardon?
We're saying that n has to be small.
Uh, right. And
But we're
that's
just saying when n is large.
right. We're not. You're right. Because in this direction, when we're looking to use a binomial, we don't want this random sample to be very big. Because look at them, how the probabilities work when we're using 10 of them.
So,
So-
we say when n is small?
Right, we want n to be less than 1/10 of the big number, so that's small. So, which makes more sense to you? I want you to pick one of these or the other. They mean the same mathematically. I think of it in my brain, I want the population to be greater than 10 times the sample. Same thing, but I'll write mine in, but you can write yours in. This is the test. All
But we're
right.
still keeping when n is large.
Yeah, when n is large, right.
What
Now this-
about
and
when
this
n is large?
This
I
is
don't.
when we say assume binomial for a simple random sample. Any simple random sample you take is not truly a bins unless it's close to these parameters where the n, the whole population is greater than 10n, which is your sample size. So when n is large, when this is the whole population, and this is the sample size. All right, we'll practice with this.
I have a question.
Uh-huh.
Why is it when n is large if we want n to be small?
We talk about little n.
Yeah.
All right. When we did this, what would it look like if n was like really big, like 5,000? What would that do to all these calculations?
It would change.
It
them.
would change them. In
But-
fact, this number would not be close to this number anymore.
So then would we want n to be small instead of when n is large?
Yeah, little n has to be small.
Then why are we writing when n is large?
Which n?
What, up right above that?
Left.
No, not like the size,
Okay,
but like
well,
that phrase.
You're right. I'm sorry. You're
It's-
right. Assume binom, it's not when n is large. I was trying to insert, it's not when n is large, is it? Let me think here. All right. Assume binomial distribution. I think I was confusing this one and that one. So assume binomial distribution when, for a simple random sample, when, right, so it's not that n is large. Sorry about that. So very good, Allie, thank you. So the population has to be greater than 10n. All right, so let's try one and see if we can verify that. You said that was on your homework, is that right? Why don't we look at that one first? What number did we have to do that on your homework? Obviously you weren't prepared to do that, so I think it was the last one. I thought that you could do number 87. On that one.
I said, are you sure about 87? And you were like, yeah.
Yeah, lots of. All right. Julia, would you read 87
Hold
for
on, I
us?
still have to get to the page.
I think you were saying, are you sure about all of them, if I remember?
I actually do remember saying that though.
About
Okay.
87?
Yeah.
Yeah.
All right.
I mean, it might have been.
4. Okay, 87. Airport security. The Transportation Security Administration, TSA, is responsible for airport safety on some flights. TSA officers randomly select passengers for an extra security check before boarding. One such flight had 76 passengers, 12 in first class and 64 in coach class. Some passengers were surprised when none of the 10 passengers chosen for screening were seated in first class. Can we use a binomial distribution to approximate this probability? Justify your answer.
All right. So first of all, I think it's only asking us to do this test. It's not really asking us to find any probabilities. It's just saying, can we assume that this SRA is a binomial? So, throwing the numbers in this test, we have to test if big N is greater than 10 times the little n. So the sample size is number 87. What's the sample? 10?
The sample is 10 and there are 76 passengers, I think.
Right. So 10 is our, 76 is our big number. Is that greater than 10 times our smaller sample size, which you said was what? 10? Yeah.
10.
All right, so is 76 greater than 100?
No.
It fails. So the answer to that one is no. Let me see what the book got. We cannot use the binomial distribution here because the sample size 10 is more than 10% of the population 76. So that's all you had to do on that one. They gave you all that information, but that's all you had to do. All right.
That was 87.
Yeah. So now we did it.
Okay.
All right, are there questions on the other ones from that? Okay, we're going to have to shut down the video. We will catch you later when you've done this